All right, it's recording. Exercise 5D. Today we're doing multiplying and dividing algebra. Last session, 5C, you were doing adding and subtracting. So here, 5D, this is where the common misconceptions happen. And so my aim is to show you the difference between the two. And it's funny because I literally said this last class and I told them where the misconception is. And by the time we did the first example, the first student I chose did the wrong thing as well. Okay, so I told them that most of the time it's about 40% of you will do the wrong thing when it comes to the test. And let's see if anyone does it today again. Okay, so here we go. Multiplication. Let's remind ourselves. When we multiply 5 times 5 times 5 times 5, I don't need to know the answer. I need to know this simplified. So we're too lazy to write 5 times 5 times 5 times 5. It takes too long. So we use a different notation. What do we do, Leon? 5 to the power 4. So it becomes an indices. So when you say 5 to the power 4, it's not 5 times 4. It's 5 times itself 4 times. Then when you compare it to this one, see they're different. They're different because one's repeated addition and the other one's repeated multiplication. When you do 5 plus 5 plus 5 plus 5, that repeated addition, we're too lazy to do that. So we then wrote a new notation to simplify that. What's another way of writing 5 plus 5 plus 5 plus 5? Yes, Liam? Very good. And that's what you would have started off with, 4 groups of 5. That's what this means. This means you've got 4 groups of 5. That's 1 group of 5. That's 2 groups, 3 groups, 4 groups. So 4 times 5 gives you 20. Was a shorter way of doing that. The other class asked me, like, why do you have to do that? Like, can't you just leave it as that? And I said, well, what if I gave you 5 to the power of 99? See, what you don't want to do, you don't want to sit there writing 5 times 5 times 5 99 times. And same thing here. They said, well, why do I have to write it as 4 times 5? Can I just leave it as 5 plus 5 plus 5? And I said the same thing. I said, well, unless you're bothered to do 99 times of 5 plus 5 plus 5 plus 5 99 times, then you do that for yourself. But we teach sort of efficiency. We teach notations to be more effective in what we're trying to communicate. So the 99 times 5 represents the 5 plus 5 99 times versus 5 to the power of 99 means you times it 99 times. Yeah, 5 times 5 times 5 times 5 times 5. Yeah? So the numbers doesn't seem to face students. It's the next one. So this is where the confusion comes in. When I just focus on the algebra, remember, a letter represents a number. We just don't know what that number is. So when we say A times A times A times A, this should be simplified to what? Let's go with Ashwin. Beautiful. A to the power 4 and not 4 times A. Okay, there's a lot of students will write this as 4 times A. It's not. That is repeated multiplication becomes A to the power 4. So write that in. Versus this one. When you're doing this one now, A plus A plus A plus A, which is what you did last session. And everyone got. But whatever, for some reason, when I start teaching 5D, they mix these two up. Happens all the time. Every single year, and I've taught for 14 years now, every single year with year 8s is without fail, I get students mix these two. So I teach 5C, everyone's like, oh yeah, too easy. And I do 5D, and there's a mix. It's really interesting how it works. There's something about this that was intuitive the first time. When I say an apple plus an apple plus an apple plus an apple, and I say how many apples are there, all of you can answer it. You would say there are 4 apples. But for whatever reason, in this exercise, as you're doing this, please check your answers. Somehow you mix these two together. It's just some wiring, the way we sort of work. When you see the times, you kind of see the plus or something. And they're actually 2 very different ones. And I said that in the last class, and then I did the first example. Literally, it was just a minute later. Here's what I did. I went, all right, team, let's do this one. And I said, I picked a student, and I just said, let's do this one. Let's simplify this, right? And I showed this. I said, here, notice it's all times, not plus. And then I said, A times A times A times A. I'm going to pick someone now. Let's go. Let's go, man. A times A times A times A. What does that simplify to? A to the power 4 is the correct answer. So A to the power 4, notice we don't collect with a B because that's not the same letters. A times B is not repeated. This is repeated. But then b times b. What is b times b? Let's go with Mandy. What's b times b? What can I rewrite that as? B to the power of 2 is correct, not 2b. A lot of students will write 2b. Notice there's the times in between. Now, we're too lazy as mathematicians. We don't write the times, so we write. Beautiful. This is what we write. So when you see this, this actually just means a to the 4 times b2. But a to the 4 just means a times a times a times a 4 times b times b, which is b squared. That's all it means. Okay, so instead of writing this line, this is much shorter. So in this exercise, you're practicing to avoid writing long expressions and you're trying to shorten it. Okay? Versus, now let's compare it to the other one. This is what you did in 5C. See how similar they are? They look similar, but they're very different. This is repeated addition now. So let's have a look at repeated addition. This here, if you're talking about apples and bananas, remember they're separated in terms of terms. How many terms are there in this expression? Can I please have, let's go with Sully, since you've done 5ABC. How many terms are there in this expression? There are 6. Okay, and how do you know? It's separated by a plus or a minus sign. So this is 1 term, 2, 3, 4, 5, 6. But the reason why you said 2 is because you already simplified it in your head. Okay, so you have to simplify this. This current expression has 6 terms. Okay, in the last exercise, you then try to reduce 6 terms down to less. Now here, there are like terms. Which ones are like terms? Can I please have Hauschwan? Which ones are like terms? A's. So all the A's, A plus A plus A plus A, those are like terms, but B's different. B's a different term. There are 2 B's. So these 2 are together and the other 4 are together. So what is A plus A plus A plus A? Yes, Solly? Very good. This becomes 4 groups of A, because remember A plus A is 4 times A, which means 4A. And the other one is B plus B, which is 2B. And this is why Sully said before it was either 6 terms or 2 terms, because in this expression now, you got 2 terms separated by a plus sign. So you went from 6 down to 2. Can you see the difference between these two? If I asked you how many terms were there in this first expression, you told me 6, which is correct. But if I asked you how many expressions there are, or how many terms are there in this expression, they're not 6. How many are there? How many are there in this very first one? It's a trick question. How many terms are there? No? So most students get confused. See, look at this one. I said separated by a plus or minus sign. You counted A separated by plus, A separated by plus. So you counted 6. How many separated? None. So how many terms are there? There's only 1. I know it looks big, but it's only 1. And that's the difference between the two. Timesing is always 1 term. Adding, subtracting makes it 2 terms. That's why it's different. When you add or subtract, you got to look for like terms to add or subtract. This one is not looking for like terms. They are just 1 term. So you can't look for another term that looks like it. This is a unique term. All you're doing is just making that term smaller. So just for 1 term, you're making it smaller. This is 1 term. It's not 2. It's a to the 4 b squared. That's 1 group. That's 1 group there. It's not 2 groups, not 3 groups. It's just the 1 big group. This is 1 group. That's a second group. Okay, and you tell by the letters. So that, I always say, you tell by how many plus or minus signs there are, it separates the term. So this one is actually 1 big term. That's 1 term. So you end up with 1 term, but it's just the shorter one. Yeah, so still 1 term. This one's 2. Whoops. 1, 1. Okay? Let's do some practice now. So we got the difference between the two. Let's do the first example practice. Here we go. Just to remind yourselves, can you write here, explain the difference between multiplication and addition? When you have repeated multiplication, it becomes powers. Okay, to remind yourself that it becomes a power. So every time you see a time symbol repeatedly, it becomes powers. Versus repeated addition, that becomes multiplication. Okay, so they're very two different ones. But
what about repeated addition? That's repeated multiple times, which becomes repeated multiple, which becomes ours.
that's right. That's how it works. That's where the theory is. So you started off, if you think about the journey of mathematics, you started in primary school learning addition, then you did the reverse of that, which is subtraction. After you learned how to add, subtract, they said, well, we add a lot. What happens if you repeatedly add? That's why you have to learn times tables. And that's where a lot of students stopped. A lot of students stopped learning their times tables or practicing, and that's where it stops there. So a lot of students know how to add. Some students are okay with subtraction, but times tables is where it separates. And then when you don't know your times tables, you got to learn the reverse, which is division. After you learn that, the next bit is once you get to year 7, we then said, well, we do a lot of timesing. We do repeated multiplication. That's when you learn indices. And that shows the difference. That's how I know. If I pick up a year 7 textbook or exercise book, I can tell if a student understands their mathematics well just based on their times tables. But that's exactly what you said. You go through a journey of mathematics. You add, then do the reverse, and you do lots of adding. Then we're like, oh, it takes too long. So you learn times tables. Then you have to learn your times tables, the reverse, then repeated multiplication, and you learn a new set of notations. Yeah, that's pretty much junior mathematics. That's what 7 to 9 is all about. It's about add, subtract, multiply, divide. Then you do squaring, so powers, square roots, percentages, ratios. That is what your basic numeracy skills that are out there when people say you need some level of numeracy for any job you need, that's what they're saying. You can do some percentages, you can do some calculations to do your budgets, your taxes, or I don't know, do some home loans or whatever it is. You need the basic just understanding how to work with numbers. And it's just add, subtract, multiply, divide. That's it. That's the most basic skills that you need. And then beyond that, that's where when I start doing algebra, it's more efficient thinking, abstract thinking, and not all of us can do that because you need foundation. And foundation means practice. The more practice you do, the better you get at it. Yeah? All right, so here we've got powers, times. Now let's do the first example. See who's going to make a mistake here. Who wants to have a go with this one? Hands up. No goers? No takers? All right, Leon, let's try this one. So I'll guide you along too. So first one, what does 2a mean? 2 times a. So I want you to break it down. For the first time, of those who aren't really confident, break it down. This means 2 times a. Then you break it again. This is your time symbol. What's 3ab mean, Leon? Very good. That means 3 times a times b, because we're too lazy to put it in times. So put it back in. Now do it again. That's times. What does 4b mean, Leon? 4 times b. Beautiful. Now once you've broken it up like this, you see with multiplication, remember the order doesn't matter. You can write it in any order because whether you do 3 times 2 or 2 times 3, the answer is still 6. So here, that looks intimidating. So what I tell my students to do is rewrite it so all of the numbers are together, all of the common letters are together, and that way it should look much easier to do. So watch what I do. I simply take Leon's description. I take all the 2s and the 3s and the 4s, all the numbers. Let's write it all at the start. 2 times 3 times 4. So I just did 2 times 3 times 4, all in order. And then I look at the letters. There's an A, so there's only 2 A's, so then I write the next one, times A times A. Times with, notice that the next one I have 1B, 1B. So I just write, let's do another color. See how that looks neater? Even though it's pretty much the same answer, but this one, most students will get it right. This one, you can miss out steps. So I always tell them to organize your thinking because that's what mathematics is. It's a problem-solving skill. You're being critical. It's like problem solving. Yeah? Puzzles. So here, if you just do the numbers, let's do it, Leon. 2 times 3 times 4? 24. So this simplifies to 24. This is where you have to remember the things I told you before. What's A times A, Leon? Good. This is A squared, not 2A. That's where the mistake comes in. It's not 2A, it's A squared. It's repeated multiplication. Next one. B times B. What is B times B, Leon? B squared. Very good. So then, remember, as mathematicians, we don't like putting the time, so your final answer should be? Beautiful. Everyone give him a clap, please. This. Beautiful. I love the enthusiasm. This is the perfect solution. Okay, this is the most common mistake that students do when I put a whole bunch together. Students mix them, they add them, they do a whole bunch of things. But if you break it apart, it's not hard. All right, let's do now the reverse. What if I do addition? Let's do addition. Let's do the comparison. Here we go. 2a plus 3ab plus 4b. How many terms are there in this expression? Can I please have... What have I chosen? Let's go with Kyle. How many terms do you see in this expression? There are 3. So there's 1, 2, 3. Now out of those 3, do I have a like term, Tom? No. Okay, so none of the groups are the same. So this is different. This is one term already, so you don't have anything to compare with. This one, there's 1, 2, 3, so you do compare. And you ask yourself, are there any terms that are the same? This one has 1a. This one has an a, but also has a b, so they're not the same groups. This one has a b, but doesn't have an a, so it's not the same groups. All 3 of them are different. And because they're different, you can't group them together. So your final answer is 2a plus 3ab plus 4b. You can't do anything to it. They're just very different. Okay, but students will feel like they need to do something to it, and they'll come up with that answer, or they do a mixture of the two. They do 2 plus 3 plus 4, and that's what? 7, 9, and they do a squared, b squared. So do a mixture. I see it all the time. I don't know why, it just happens. So 5C, you don't have troubles, but you get to 5D, this happens. So I'm doing a very clear contrast so that when you do them, be careful. Count the number of terms. Yeah, that's why 5A was important, but you had to understand how many terms there are. This is just 1. Nothing to compare. This is 3, separated by a plus and minus sign. Yeah? Let's try another one. Flip over. Okay, so you've done times. Now this is the same idea. Times and dividers just opposites of one another, but same thing. I want you to break it apart. So here we go. Let's remind ourselves. What's 5 divided by 5, which means 5 over 5? What does that equal to? 1. A lot of students tell me 0. And I'll tell you why students learn it this way. You know, back in maybe in primary school, your teachers might have taught you this. You see that? A lot of teachers teach when you're simplifying fractions. They go, if the top number and bottom number is the same, you can just cross off. Hands up if you've been taught that way. Yeah? Okay, it's meant to be a quicker way. But when you cross them off, you see if you do that, the answer is 5. That's correct. But when you cross them off, the teachers need to explain to you, or you need to understand, that's not 0. It doesn't just disappear. What actually happens is you're actually doing 5 divided by 5, so it's 5 over 5, times 5 over 5 again, and then times, and you still have 1 5 on the top. See what's happening? There's 3 5s on the top, 1, 2, 3, and there's 2 on the bottom, 1, 2, 1, 2. So what's missing here, that's 5 as a fraction is 5 over 1. But what you just told me before, what's 5 divided by 5? It's not 0, it's 1. So what you're really doing is you're doing 1 times 5. That's why the answer is 5. But the way the teachers back then would have taught it, they cross it off, and so students think it just disappears like magic or something, and it just becomes 0. But the reason why that's a problem is by the time you get to year 9, year 10, year 11, and I give this problem, that's how I know straight away how strong your algebra is, or your number sense. I give them something like this. And this is what students do. They follow exactly what they learned in primary school. They see X, they see an X, and they'll do this. But you can't do that. Okay, you cannot cross that off. And the reason why is because it's not dividing. It has to be times. There's a plus here. You can't just cross off a number. Yeah, and I can prove it by saying, let's say if I did this, let's say that expression, let's think about a proof to this. If I cross that off, the answer is 1. Right? If I cross it off, the answer is 1 because there's only 1 left over. True? But if you actually test it, let's make up a number for x. If I did this now, I put a 5 there and a 5 there. 5 over, or 5 divided by 5 plus 1 is actually the same as saying 5 over 6. 5 over 6 is not the same as 1. So you can't just cross and say that works. It doesn't. But it works if I didn't have the plus. if you didn't have that plus, if you had a times 1, that would have been okay. That actually would work. If it was a times, not a plus, 5 over 5 crosses out to be 1, then 1 divided by 1 is 1. That is true. It works out. But the only logic to that is because students don't realize you only cross off because you're doing division, and division is the opposite of times. That's why it works. But if you have addition, why are you suddenly doing division? Doesn't make sense. So that's why at year 9, year 10, year 11, they make a lot of mistakes here because it was taught wrong. So I try to teach you the right way. It's a bit longer, but it is the right way to do it. And the better you do it, the more structural your foundation is. Yeah. So here, when you're doing these algebra, I need you to understand that 5 divided by 5 is 1. Then that means A divided by A is also 1. It's the same thing. A over A, whatever that number is, 5 on 5 or 6 on 6, will always equal 1. That means when you're doing this side over here, you don't just cross things off just because you do. You have to understand it's actually A divided by A because they're all times. So the inverse of all of them, A divided by A divided by A, they actually become 1. Now, I want you to actually write this fraction. Don't just do this crossing until you get really good at your algebra. I want you to do it this way. I want you to count how many A's there are on the top, and I want you to write it out. So A times A times A. Separate it. I know it takes long, but it really trains your fractions and your layout. How many A's are there on the bottom? 2. So then you write 2 of them. There we go. So I've done exactly the same. What's missing on the third one? 1. Because it was just 1A. That's the same thing as writing A over 1. Because A times 1 is still A times A. And A times A, I still have it on top. So it's no different. But by separating it, we all know what's A divided by A again? 1. This crosses out to be 1. What's A divided by A again? 1. So if you put it all together, it's just saying 1 times A, because A over 1 is A. 1 times A, what does that become? A. So that's how I want you to do it. I don't want you to do it this way. And then say the leftover answer is A. I know it's quicker, but then you're training yourself to understand something wrong. You understand the basics, then you can start doing shortcuts. Okay, don't do shortcuts without learning. Otherwise, maths becomes magic and not logic. All right, it's always black and white. There's a reason why things work. It's not something that you memorize. Yeah. All right, let's try this one now. Last 2 examples. Here we go. Let's copy this. I want you to break them all apart. So let's do the top together. 10AB. What does 10AB mean? Can I please have? Let's go with Hauschwan. What's 10AB mean? Beautiful. 10 times A times B. Very good. What does 15 BC mean? Can I please have Sienna? Beautiful. Now you've got all the times. Separate it. Yep. Split it up. Numbers with numbers. Common letters with common letters. And it makes it easier. So this is what I would have done. 10 over 15. Those are the numbers. I've got one A on the top. So I leave it as an A on the top. Times, I've got one B on the top, and I've got one B on the bottom. So I just copy literally what I have. I just separate them. Because remember, times doesn't matter about the order. You can write any order. And then last one is I've got a C on the bottom. You see, at the end of the day, it's 15 times something times B times C has to be this. So what number must go here to make it still the same? 1. So I put a 1 here. 1, 1. And it doesn't change it. 10 times A times B times 1 will still give you 10 times A times B. 15 times 1 times B times C still gives you 15BC. But once you split it all up, isn't it so much easier? You can see B divided by B we know is 1. And this one you did last term. Find a common factor of 10 and 15. And then you can times them together, which I'll do. Sully.
So it's because they're not like terms. So you have to find. So 1 is in one place.
The reason why we put a 1 there is because when you multiply fractions, we always do top with top and bottom with bottom, right? So you see the top expression, 10 times A times B, I've got it up here, but with this an extra C, I have to have a number up here that doesn't change that expression. And every time you times 1, it doesn't change anything. So that's why we put a 1 there, just to make it separate, that we can see this fraction times this fraction times this fraction times that fraction does not actually look different to that one. This is just the more expanded version. It makes it clearer why you do it. Whereas most teachers normally teach it, they simply teach you to go, B's cross out, 10 and 15 is 2 and 3, and then your answer is 2A, 3C. Okay, I know that's quicker, but that's where the mistakes happen by the time I teach 9, 10s, and 11s. Yeah? So I want you to see where the logic comes from. It always has to be a times. No plus in between. Yeah? All right, here we go. So let's answer the question. B divided by B. What's B divided by B again? 1. So this becomes 1. B divided by B is 1. 10 over 15. Simplify that. What's a common factor? 5. So 5 goes into 10 twice, and 5 goes into 15 3 times. Times, and notice I keep every fraction the same. I'm going to rewrite it again as 1 over 1 times 1 over C. So what I'm doing? B divided by B is 1, and 1 as a fraction is 1 over 1. That's still A over 1. That's now reduced down to 2 over 3, because we found out 5 goes into 10, 5 goes into 15. And over here, 1 over C. So I haven't changed anything, I just made it smaller. Now, when you're multiplying fractions, remember from last term, top with top, bottom with bottom. So you're going to do 2 times A times 1 times 1. Let's work that out. What's 2 times A times 1 times 1? Can I please have Ashwin? Beautiful. It's just 2A. 2 times A is 2A. 2A times 1 is itself. And times 1 again is itself. So it's 2A. Just do the bottom. What is 3 times 1 times 1 times C? Can I please have... Yes, Ashwin again. 3C. And that's as simplified as you can get. All right? I'm going to pause the video. I want you to have a go with this next example by breaking it apart. But I'm going to break it up first. And then I want you to do this step. Okay, so here we go. I'm going to pause the video. This is what you should have got. Here we go. I'm going to unfreeze. Here we go. So what I did is I literally counted the A's. There are 3 A's on the top, 3 A's on the top. There are 2 B's on the top, 2 B's on the top, 1 C on the top. Then I counted the bottom. 1 A on the bottom. Since there's 2 A's, I left it blank. And then I went to the next one. There's 2 B's on the bottom, so I followed the 2 B's. 3 C's on the bottom, so here we go. I added the 3 C's. So all the gaps that's missing, all you have to fill up is just the 1s, because that doesn't change the equation. But what's beautiful is once you split it up, it's really straightforward. A divided by A, we all knew, was 1. B divided by B is also 1. 1, 1. That's why they all change to 1s. So really at the end of the day, when you're doing timesing, you're just timesing the top. 1 times A times 1 times 1 times 1 times 1 times 1. What does the numerator give you? A to the power 2. Very good. Not 2A. Beautiful. And same thing here. 1 times 1 times 1 is all 1. But then C times C is C squared. What you're doing there is actually the same repetition that year 9s do, year 10s do, year 11s do. I literally have been teaching this for like 3-4 years ever since year 8. It's just the same thing over and over. Watch, this is what my year 11s are doing.